This is the next video for section 3.1, limits. Last time, we learned what limits were. We learned how to visualize them and how to see them, right? What we're going to do now is learn how to solve them using techniques without graphs. Now, remember, at the end of the last video, we said, well, wait a minute, to find the limit, we can just plug in the value. All right, and that's what we're going to do. Limit as x approaches 0 of x squared plus x minus 2. Well, all we need to do is write our m's properly, and then just plug in 0 for x. So we get 0 squared plus 0 minus 2 equals negative 2. That's our answer. No need to use graphs, no need to plug in values close to 0. Just plug it in. Done. Similarly for number 2, all we're going to do is plug in x equals 1. Right, and we get 0. That's the limit as x approaches 1. We can do one more example. And this is going to give us negative 2 over negative 2 squared plus 2, which reduces to negative 1/3. Okay? Now, what about something a little more complicated, a little more annoying, like this example right here, where we plugged in our number and we got a non-zero number over 0? Let's learn how to solve that. In fact, let's use that example. Let's consider the limit as x approaches 1 of x squared plus 5 over x squared minus 1. Now, one thing to keep in mind, I like to plug in the number, like I like to plug in 1, and we get a non-zero number over 0, which if you remember, I'm sure you remembered from like middle school or elementary school or something, maybe high school, you're not allowed to do that. You're not allowed to divide by 0. Why not? Well, division's just not defined that way, but it's not defined that way because your answer is going to be infinite. If your numerator is just constant and your denominator becomes arbitrarily small, then your number gets bigger and bigger and bigger. So we know that this limit is infinite. The only question is it infinite in the positive direction or is it infinite in the negative direction? Or maybe both, I guess, because there are left and right-hand limits. And so in order to see that, we need to break it down into its left and right-hand limit components. So let's do that. Let's say, okay, we've got the, all right, LH. Right, let's take a look at the left-hand limit. The limit as x approaches 1 from the left, x squared plus 5, x squared minus 1. Well, again, we know we're going to get 6 in the numerator. That's not the concern. The concern is what's happening in the denominator. And what we're trying to do is we're trying to see whether the denominator is less than 0 or greater than 0. Right? Because remember, x never reaches 1. So if x is approaching 1 from the left, then we know that x is less than 1. And if you think about it, if x is between 0 and 1, and you square it, you get a number that's even a little bit lower, right? So that implies that x squared minus 1 is actually less than 0, right? Because you're taking a number less than 1, you're squaring it, which means it's still less than 1, and then you're subtracting 1, so now it's negative. So what this means is that the limit is that of x approaching 1 from the left, of x squared plus 5 over x squared minus 1, well, we've got a positive number over here, we have a negative number over there, and so we're going to get negative infinity. Right, because a positive divided by a negative equals a negative. Okay? Let's take a look at the right-hand side. Limit as x approaches 1 from the right of this same function. What are we going to get? Well, now we're considering x greater than 1. And that means, if you think about it, like 1.01, for example, if you square it and subtract 1, you're going to get something a little bit bigger than 0 for the same reason as before, but it's the opposite, right? And that means that we're getting a positive over a positive. Let me here. So limit as x approaches 1 from the right is going to be positive infinity. Sometimes math teachers prefer you to write positive infinity. I don't really care. So hold on a second. The left-hand limit was negative infinity. The right-hand limit was positive infinity. And again, we got that positive infinity because positive over positive equals positive. So the double-sided limit does not exist. Okay. Whenever you get a non-zero number over 0, your limit will not exist. But you can't just say it doesn't exist. You have to look at the left and right-hand components. Now, what I will just say is I spent a lot of time doing that. Some of you might have immediately seen that we were going to get negative infinity once you saw the positive over negative trick, right? So you don't need to do all this stuff right here. You just need to do this. You can just state your answer. You just need to do that. State your answer. And then, of course, you also need to do this. But that's it. Okay? That's what you really need to do. Let's try some other examples. Okay? Here, let's see, we have x approaching 2. So what happens when we plug this in? So remember, looking for like a non-zero number over 0. I think we're getting 0 over 0. Okay, that's where we'll come back to that one. X approaches 3. Plug that one in. I think we also get 0. Weird. Let's go back to blue, actually. Okay. What about this guy? This guy, I think is legit, right? We're gonna get limit as x approaches 3 of x plus 4, x squared minus 3. That's gonna equal 7 over 6. Yay. Okay, I'm not sure about 1 and 2. This is a new situation. We have 0 over 0. So let's investigate further. Well, if we take a look with our calculators, we go back, or in this case, Desmos. You can use a calculator, but I think Desmos is way superior. What happens? We have x squared minus x minus 2 over that. Okay. So I'm going to open up Desmos once again. And there we go. And let's get rid of this. And why don't we just use a new graph? There we go. So let's say f of x equals this parenthesis. So it's x squared minus x minus 2 divided by x squared minus 4x plus 4 is what I think it was. Okay. So let's plug in our values and see what we get. F of, now we were interested in what, 2, right? As x approaches 2. So let's do f of 1.9, 9. Oh boy, okay. What about f of 2.1? 0, 1, 0, 0. Wow, okay. So it looks like we've got a divergent answer, right? This is negative 29, I think. Did I get that right? Yeah, negative 29. What happened when I went up here? Negative 299. Okay, right, yeah. This is negative 31. This is negative 301. Okay. So it looks like this limit, let me cross this out right here, because this limit does not exist. Okay, and then meanwhile, let's take a look at this guy over here. So let's try, I don't know, g of x is going to equal, what's that, x squared plus 2x minus 15? There you go. Okay. So we have this. Okay. Now let's see what happens if we plug in numbers close to 3. So we'll say g of 2.9. Okay, looks like that's getting close to 8. G of 3.01. Okay, well, looks like we have a different answer going on over here. Right here it looks like we're getting 7.9, 7.99. Here it looks like we're getting 8.1, 8.01. So here it looks like the answer is 8. So it looks like if we get 0 over 0, it really doesn't give us any clue as to whether our answer is going to exist or not. And in fact, 0 over 0 is an indeterminate form. Meaning we must do more work to find the limit. Okay. So how are we going to do this? I don't want to keep plugging stuff in. Well, if you notice, in both of these cases, we can factor the top and bottom, right, numerator and denominator, of our expressions. Okay, so let's do that over here. In this case, limit as x approaches 2, but I'm going to factor the top, and if you notice, it's going to be x minus 2 times x plus 1, all over x minus 2 times x minus 2. See how I just factored them? And then you notice, oh, look, these cancel out. And at this point, we're left with a situation where when we plug in x equals 2, we get 3 over 0. And we know what that means, right? We break this into our left-hand limit. Limit as x approaches 2 from the left of x plus 1 over x minus 2. And I'm just going to jump right to the answer. If x is a little bit less than 2, then x minus 2 is less than 0, x plus 1 is greater than 0, and we get negative infinity. Right hand, we're going to be getting, right, x plus 1 over x minus 2. The opposite's going to happen. And so sure enough, this limit as x approaches 2, you can just write the factored form, does not exist. Right, so this was actually an easier expression than we realized. We just needed to factor out that extra copy of x minus 2 in the numerator and denominator. Now, contrast that with this situation, right, where we have the limit as x approaches 3, but I'm going to factor the top. And if you'll notice, I'm going to get x plus 5, x minus 3. All over x minus 3. And now that I factor the top, I can divide out by a common factor. And now I can just plug in 3 and get 8. Oh, that's our answer. So again, this expression was much more complicated than it needed to be. But we didn't notice that until we factored the top. So we've got some practice problems here, but I'll leave this for guided practice. We'll stop here.